All right, so the purpose of this last video is actually just a little recap of the factors notes if you were not able to get them well or you just want to verify some things. The first four were actually verified already independently, but in case you wanted to, you can watch this little optional video. It doesn't do anything extra than what we've already been doing or than what you already have the opportunity to do is follow those slides for Kinetics to fill it in. But it just kind of gives you a nice, I guess, a good feeling knowing that you got the right things, or in case you're worried about it. So, without further ado, there's the factors affecting rate of chemical reaction, which you were poised to go collect in the notes sheet. Remember that note sheet is attached to this day 2 or day 1 of the factors announcement. So we have a reaction rate factor, what it is exactly, the name of it, that is, what is it, what happens, and then an example. Consider the reaction between zinc and hydrochloric acid. So concentration is the first one, concentration. Okay, consider this reaction. There are more particles of acid per unit volume in the 2 molar than the 1 molar acid, so there'll be more collisions between the acid and zinc particles. So what is it? Concentration. Sorry about that, had a little delivery. Good deal. By the way, Merry Christmas, of course. So how does concentration affect the rate? More concentration means more collisions. So that's what is it. So more concentration means there's more reactants to react. That's what it is. What happens then is that more concentration, okay, more reactants means more collisions, more chances for collision. Okay. So more collision, this is what it is. Okay, more collisions means faster reaction. So we would say here, higher concentration equals more collisions equals faster reaction. The big red box kind of tells you a good synopsis as to what actually happens. Okay, an example, they give it to you right here. 2 molar HCl acid versus 1 molar. 2 molar HCl would yield a faster reaction with the base, for example, because more hydrogen. If we had the same amount of base or the same amount of zinc, okay, in this case, same amount of zinc in each one, but a higher concentration of HCl, faster reaction due to the concentration. Cool. Surface area. Solids break apart. Same thing is similar with solvation. Okay, so what is it? Surface area. Or name of it, surface area. What is it? Particles, reactants are broken down ahead of time. Okay, they're broken down. They're powdered instead of chunked, right? Powdered reactants would be smaller particle reactants, right? Powdered sugar versus granulated sugar. So the powdered mixture of smaller reactant particles at a time, that's what it is. Okay, smaller particles, excuse me, actually what it is smaller particles means more surface area to react with other reactants, to collide with, right? Better surfaces to react with, better surfaces to collide with, more surfaces to collide with. So that's what it is. Smaller particles means more surface area to collide with. What happens? More surface area to collide with, better and more collisions, faster reaction. So more surface area yields a larger and faster reaction. Larger surface area. Smaller particles, more surface area. More surface area means faster reaction because there's better collisions. So that's what happens as well, better collisions. Wherever you include about the collisions mentioned is either the what or the how is fine. The example here would be that you can dissolve, let's say you're making some sort of creamy frosting of some sort. If you want to do like a homemade frosting that's more royal frosting, you wouldn't use granulated sugar to dissolve in your butter and a milk mixture. You'd want to use granulated to make it smoother and dissolve faster in that substance. Even if you heat it up, it'll dissolve faster, it'll move faster, react faster. Same thing in the case over on the other reaction. You could say if the zinc were chopped into smaller pieces, the HCl could, higher concentration HCl, doesn't matter. The smaller piece zinc would actually react faster. Any example you can think of, the solvation process you can use, even though it's technically not a chemical reaction. Temperature, just based on the kinetic molecular theory. The kinetic theory means that temperature means is the average kinetic energy of particles. So if you increase temperature, you're increasing the kinetic energy. Kinetic energy is the energy of motion. So temperature is the name. What is it? It is the measure of kinetic energy of particles, or quote in parentheses, energy of motion. What happens? More temperature, faster motion. Faster motion means better collisions or more collisions, therefore faster reactions. Higher temperature equals faster motion, more collisions, and thus faster reaction. Those are kind of the blend of the what is it and what happens. Mainly that stepwise part is the what happens. Bottom line reaction is that higher temperature makes a faster reaction. Effect of a catalyst. A catalyst is a substance that somehow facilitates the reaction of the two reactants. It facilitates the collision. It gives the collision a safer place to react. And because of that safety, there's not as much energy that's required. So it literally speeds the reaction along and decreases the activation energy. So number 4 here, this is catalyst. What is it? It is a substance that increases the speed of reaction and it never gets used up. Okay. How does it do it, or what is happening? It increases improves the conditions for the reactants to collide. It creates the right conditions for the collision. It makes the conditions for collision better suited to react. Okay. It basically hosts the collision in a better environment, in a safer environment. And what that means is hosting the collision, the catalyst hosts the collision, which means it decreases the energy required for the collision, lowering the activation energy so the reaction is easier to proceed as it goes. So notice here's where we can see it in the exothermic reaction. It lowers the activation energy required, so it could require, instead of a match light, it could be just a friction, a little bit of friction added to get the reaction going. Okay, so catalyst leads to a faster reaction. Make sure you have that box there in the what happens portion. All right, those rates apply, and there's a summary of it. The example of a catalyst, we could talk about the platinum as a catalytic converter in engines to allow for the reactions of the explosive reaction of the inside the piston to generate the power that moves inside the engine. You could talk about catalysts like meat tenderizers. They literally break down some of the protein ahead of time. Catalysts that speed things up in any sort of capacity that you can think of. You can come up with your own example, or Google one would also be good. Okay, so there they are. There's another synopsis of it in case you didn't see it before. Okay, and we had the practices, and we had 5, 6, and 7 left. Gas reaction with pressure. If you increase the pressure, it makes a fast reaction. So number 5, pressure. What is it? It is you're basically squeezing the tension of the reactants. As you squeeze them, you're essentially forcing them into a higher collision encounters. They're more decisively going to collide. They're more suited to collide. So increase the pressure, you increase the proximity. That's what it is. Okay. So what happens is higher pressure, more collisions, greater chance of collisions. More collisions makes faster reaction. Cool. Orientation. When the collisions happen, some of the collisions don't have enough energy because there's also the wrong orientation. They could collide with almost the right amount of energy, but if they're not oriented when they collide right, they won't actually produce right. So it depends on how the products are formed. If the products need to be are clunkier or larger molecules, then they are better suited in a different arrangement. The better they are arranged towards looking close to the product's format, how the products will end up being. Like this example here shows, the products are going to end up being in two AB molecules. So if the AA molecule strikes right up against the BB molecule and you have an A next to a B and an A next to a B, then they're already apt to be in the product arrangement. So they're already in the AB format. Okay. If instead they collide next to each other, well, only one of them might collide, but that may not be provide enough energy to actually make the collision worthwhile and effective. So orientation and efficiency of these molecular collisions. The collisions are basically colliding in the right way in three-dimensional space. Anyway, orientation. What is it? How the reactants collide, the way they collide, and what happens if they collide in certain ways versus other in three-dimensional space. They produce products better, which would be increasing the rate. The nature of the reactants, if the reactants and components are in the same phase, liquid and liquid, gas and gas, solid and solid, they react at a greater rate, typically. So once again, number 7, nature. What is it? The phase, or if it's dissolved or not, or how the substances are brought to the reaction chamber. is what it is. What happens is matching natures means faster reaction. It's just how that goes. It increases the reaction rate. So there it is. That concludes the reaction rate notes, and hopefully it was beneficial to you. If not, well, this was totally optional. But once again, thanks for watching. Merry Christmas, and if this is the last video before I see you in January, Happy New Year, and we'll see you around. Go Dogs, don't you know it?